I'm going to create a video showing you guys how to do the work for Lab 14 on Hubble's expansion of the universe. So this is what the Lab 14 page looks like for me when I open it. I've kind of squished the pages so that both things will fit on your screen. When you can print by clicking here, and it will print all of these instructions in a Word document. You can click here on the Hubble's Law spreadsheet, and it will download this blank Hubble's Law spreadsheet. As you can see, it's not really blank, but there's lots of stuff for you to put in. Then click here on Galaxy List, and it opens a page that looks like this. So the instructions tell you to start with 2903 because that is the first one that's nicely visible as a spiral galaxy. So we can see the bulge, and then we have two arms. One comes around here and all the way out, and one comes around here and all the way out. So you start by finding the longest diameter for the galaxy. So in this case, it's right along here. And we want to click at the farthest point out that we can identify for each galaxy. And so I just clicked there, and now there are values here. And now that I clicked up here, don't click anywhere else until you come down here and click on the farthest other end of that diameter. And see, it moved the screen, but we have information. So we come over here to our spreadsheet. This is galaxy number 2903. And then click here, and you look over here on the data that was just created for us, x1, y1, x2, y2, angular size. So x1, we type in 174. y1, we type in 84. x2 is 348. y2 is 414. And that gives us an angular size of 3.4695, which matches 3.469. So we're done. Now we click back until we get back to this. Now, NGC 2903, we need to make sure that you always click on the right line. So now we're looking at the spectra. So let me open this out a little bit. If you collect spectra from this galaxy, we end up with this light curve. And so this by itself does not give us a whole lot of information. However, for calcium, the K and H peaks in the lab measure here and here. And so we have a galaxy that is moving away from us, so it is red shifted. So we find the two first strong, these are called peaks, dips, peaks, just to the right of calcium K and calcium H. So we come here to the bottom of this one and click, and it gives us a wavelength. So 3941.2. So calcium K at rest, we have already collected this data. But now calcium K measured, that is that piece of information that I just showed you, 3941.2. So we type this in, 3941.2. And the spreadsheet is set to calculate. And so the redshift for calcium K is 0.0019. We come over and we do the same thing for the H peak. And click. So 3975.3. So I type this in, 3975.3. And so the redshift of calcium H, 0.0017. So at a different part in this spectra, we also find hydrogen alpha peak. And so we click over here on hydrogen alpha, 6575.7. And so what we're measuring is where along this axis. So it doesn't matter. I could click here or here or here. It would all give me the same angstrom. I simply come up here and stick the little finger on the point to make certain that I know exactly where I am. And so this goes into the hydrogen alpha measured, 6575.7. And so redshift for the hydrogen alpha, 0.0020. So these three are fairly close to each other, so I feel like I've done a good job. So we average the three of them, 0.00186. So the angular size, based on the fact that spiral galaxies as an average at a kiloparsec are 22 kiloparsecs across. There we go, as an average. So we can guesstimate intelligently that this galaxy is 6 megaparsecs from us, and then the redshift times the speed of light gives us our average redshift times the speed of light gives us a radial velocity for that galaxy, 559 kilometers per second. So we go through, now we go, why won't it let me see that back, and look through the images, find 10 that you like, fill in, go and measure the diameter for each of them, and then measure the redshift for each of them. And so as you go down, this will fill in. And so you will end up with a graph. Currently, I only have one galaxy on the graph. Once it is full, then you will see something that looks like file, open recent. Just open. I meant to have this one sitting open ready for you. So I have filled mine in with pieces, and so I have distances, and what we end up with is a chart. So the chart shows 10 galaxies and their distance from the Milky Way and their radial velocity compared to us. So then you right click and you click on one of the dots, right click on one of the dots, add trend line. You want it to be linear. Set the intercept at 0, 0 and display the equation. I'm going to close this because I do not want to add another, but I did anyway. Trend line 2, delete. So when you do that, the trend line will appear and the chart or the equation. So remember from algebra, the slope of a line, it is represented by the formula y equals mx plus b. So m is the number that we're interested in, the slope. So 81.212. So you'll come up here and m equals 81.212. And then you take that and divide it by 3.09 times 10 to the negative 19, or 10 to the 19. You can type that in, 3.09, 10 to the 19. And so you multiply this times that. So here is the age of the universe in kilometers per second per milliparsec. Well, we need to get that down into just seconds. So we divide by the number of seconds in the year, and we end up with an age for the universe. This time, when I did it, 8.8 times 10 to the negative 11. So what that means is that from the data I just measured, that the universe is 8 times 10 to the negative 11 years old. So how old is that in scientific notation? So that is 80 billion years. So obviously my calculations are not excellent. I have done this better. I have gotten it within 3 or 4 billion years, but it's not easy to do. So I want you to do this using, okay, don't save. I don't want that. Okay. So the chart is already built for you. All of the formulas are in here, so we can see that, you know, to average 3, you're just pulling those 3 bits of data and dividing by 3. So everything is built for you in here. You simply have to do the recording of data. And so I'm going to let you do it.